We all do it every single day. Mapping out your commute, tackling a big project at work, or even just figuring out dinner. Planning, it's just fundamental.
Absolutely. It's how we manage everything.
But here's the thing, right? How often do you really have all the information you need before you start?
Almost never, I'd say.
And how often do things go exactly as planned?
Huh. Yeah, that's $1 million question. Things always seem to go sideways.
Exactly. So imagine, just for a second, a system that could create a reliable plan, one that actually anticipates and adapts to all that uncertainty.
Well, that's precisely what we're digging into today. We're looking at some really fascinating research from Texas Tech University's Computer Science Department.
Okay.
It's a paper called Encoding Conformant Planning in a Prologue by Michael Gelfand and A. Ricardo Morales. It tackles exactly that challenge.
All right, so our mission for this deep dive is to unpack how this paper introduces this powerful way to design, what do they call them? Provably correct and...
Elaboration-tolerant planning systems. Yeah.
Right. So we want to figure out what those terms actually mean, how they pull it off using something called answer set programming.
Which we'll definitely get into.
And, why these capabilities are so important for building smarter, more adaptable AI.
Exactly. It's pretty foundational stuff.
So let's start with the core problem, conformant planning. You mentioned traditional planning often assumes a lot.
Yeah, traditional approaches often assume, well, two big things. One, deterministic domains, meaning actions always do exactly what you expect.
Predictable outcomes.
Right. And two, complete initial situations. Everything about the world right at the start, no hidden surprises.
Which, as we said, isn't very realistic.
Not at all. So conformant planning is about removing those restrictions. It deals with situations where you don't know everything initially.
The incomplete information part.
Exactly. And situations where actions might be non-deterministic, their outcomes aren't always guaranteed.
Okay, so the action itself could have multiple possible results.
Precisely. It's a big shift towards AI that can handle the messy, unpredictable real world, not just follow a perfect script.
That makes sense. Building in robustness. So in this kind of messy world, how do they even define what counts as a solution? What makes a plan actually work?
Good question. It starts with this idea of a partial state. Think of it as just the collection of facts you do know at a certain point.
Okay.
They use what are called fluent literals for this, basically. Things that can be true or false about the world, like clogged toilet could be true, or armed package, meaning a package is not armed. These are the facts.
The building blocks of the world state.
Right. Now, for an action to be considered safe in one of these partial states, this is key. It has to be executable in every possible complete state that's consistent with what you know.
Wow. Okay, so even if there are unknown details, the action has to be okay regardless of how those unknowns turn out.
Exactly. It has to work no matter which version of reality, consistent with your partial knowledge, is actually true.
That sounds demanding.
It is. And then, for a whole sequence of actions, what they call a chain of events, to be a solution, it has to meet two criteria.
Right.
One, it has to be safe right from the start in your initial partial situation. And two, every possible outcome of executing that chain, considering all the initial unknowns and any non-deterministic action effects, must lead to your goal being satisfied.
So success is guaranteed, no matter the uncertainties along the way.
That's the goal. It's about finding a plan that's robust against all the things you don't know or can't perfectly control.
That's a powerful promise. But how do you actually build a system that can reason like that? The paper mentions answer set programming, ASP. What is that exactly? Is it like normal programming?
Well, it's different. ASP is a form of declarative programming. So instead of writing step-by-step instructions telling the computer how to solve the problem.
Like an algorithm.
Right. Instead, you describe the problem itself. You lay out the rules, the constraints, the goals, using a specific logic programming language called a Prologue.
A Prologue.
Okay. Yeah, it's tailored for this kind of knowledge representation. So you describe the puzzle, essentially.
And the system figures out the solution.
Exactly. The task boils down to finding the answer sets of the a Prologue program you wrote. These answer sets represent the valid solutions or configurations. And there are dedicated, very efficient answer set solvers that compute these sets for you.
So it's like describing Sudoku rules in the starting grid, and the solver just gives you the completed, valid puzzles.
That's a great analogy, actually. Yeah, you state the problem, the solver finds the solutions that fit the rules.
Okay, ASP is the engine. But how do they describe the planning part? The actions, the states. The paper talks about action language AL.
Right. AL is the language they use to model the planning domain itself. You can think of it as defining a kind of map, a transition diagram.
Where states are points on the map.
Exactly. Nodes are possible states of the world, and the arcs between them are the actions that move you from one state to another.
Makes sense.
AL has some core components. There's the signature, which lists the fluents, those things that change, like armed package.
The facts that can be true or false.
Yes. And the elementary actions, the basic things you can do, like dunk, package, toilet.
And I think you mentioned you can combine actions, like doing two things at once.
You can, yeah. They call those compound actions.
Yeah,
so maybe
right.
dunk, P1T, dunk, P2T, if the rules allow dunking two packages in the same toilet simultaneously.
Okay. So what kinds of rules or statements does AL use?
There are three main types. First is the dynamic causal law. E causes L if P.
Okay, break that down.
It means if you perform elementary action E when condition P is true, then fluent L will become true in the next state.
Cause and effect, like dunk PA causes arm T, dunking disarms the package.
Precisely. The second type is a state constraint, L if P.
So this isn't about actions.
No, this is a rule about how the world has to be in any valid state. If P is true, then L must also be true in that same state. Like maybe clogged, toilet 2. If one toilet's clogged, the other one automatically is too.
Like a dependency. Got it. And the third?
The third is an executability condition. Impossible A if P. Pretty straightforward action. A simply cannot be performed if condition P holds.
Like impossible dunk, P-E, if clogged.
Can't dunk in a clogged toilet.
Exactly. Those three statement types let you describe the dynamics and limitations of your planning world.
There was a point about deterministic domains, something called SC restricted.
Ah, yes. That's an important technical point. If your state constraints, L if P, are simple enough specifically, if the condition P contains at most one fluent literal, they call it SC restricted.
Okay. And why does that matter?
Because if your action description meets that SC restricted condition, the paper shows the domain is guaranteed to be deterministic. For any given state and action, there's only one possible resulting state. So it simplifies things. Guarantees predictability in the rules themselves, even if the initial state is uncertain.
Exactly. It's a condition that helps ensure the underlying mechanics are predictable, which is crucial for the correctness proofs later on.
Okay, this is getting clear. Let's make it really concrete. The paper uses this great example, the bomb in the toilet. Kind of memorable.
It really is.
Yeah.
And it illustrates the concepts perfectly. So imagine you've got, say, two toilets, T1 and T2, and two packages, P1 and P2.
Right.
Now, the critical piece of uncertainty, one of these packages, P1 or P2, contains a bomb. But you don't know which one.
Okay, the classic conformant problem set up incomplete information.
Right. Your goal is simple. Disarm the bomb. And the only way to do that is to dunk the package containing the bomb into a toilet.
And dunking has side effects, right?
It does. Dunking a package clogs the toilet it was dunked in.
Makes sense.
And you can unclog a toilet by flushing it.
Okay.
But there are rules. You can only dunk one package at a time into any single toilet, and only if that toilet isn't already clogged.
Standard toilet etiquette, basically.
Huh. You can say that.
Yeah.
So how would you model this in AL? They'll call this model TD0.
Let's hear.
Well, you'd have dunk, P-E, causes armed. Dunking disarms.
Got it.
Dunk, P-key, causes clogged E. Dunking clogs the toilet E.
Okay.
Flush E, causes clogged E. Flushing unclogs.
Simplug.
Then the restrictions.
Yeah.
Impossible dunk, P-E flushed. Can't dunk if it's clogged.
Right.
And you can't do certain things at the same time, like impossible dunk, P-E flush, E. No dunking and flushing the same toilet simultaneously.
Makes sense.
Impossible dunk, P1E, dunk, P2E. Can't dunk two different packages in the same toilet at once.
One package per dunk.
And impossible dunk, P-E1, dunk, P-E2. Can't dunk the same package in two different toilets simultaneously. That'd be weird.
Physically impossible, yeah.
So that's the basic setup in AL.
And the conformant part here is really emphasized because you have to find a sequence of dunks and flushes that guarantees the bomb is disarmed without knowing beforehand if it's in P1 or P2.
Exactly. That's the core challenge. And importantly, this TD0 description they use, it actually has no state constraints at all.
Oh, right. So it's trivially SC restricted.
Correct. Which means it describes a deterministic domain, fitting nicely with their theoretical framework.
Okay, so you've modeled the problem in AL. How do you feed this into the answer set programming machinery we talked about? How does the translation work?
That's where this cautious encoding method comes in. They translate the entire planning problem, the AL description, the initial state, the goal, into one A prologue program, which they call E.
Right, EP. And you said it has different parts.
It does. It's structured. First, there's ED. This part takes your AL action description, all those causes, if, and impossible rules, and converts them into A prologue rules.
Okay.
A key piece here is the inertia axiom. It's a fundamental rule in representing action and change. It basically says things stay the same unless some action explicitly changes them.
The default is persistence.
Exactly, like HLT plus 1, HLT, not ABLT.
Yeah.
This means fluent L holds at the next time step T plus 1 if it held at time T, and it wasn't made false, aborted, or changed by an action at time T.
Makes sense. Keep things the same unless forced to change. What else is in it, Till?
And you have E, S arrow. This part represents your initial state specifically, the partial initial state. For any facts you know are true initially, you add rules like A, S arrow, meaning fluent L holds at time 0.
So you encode what you do know.
Right. And finally, there's ESF, which encodes the goal. This includes rules to check if the goal condition is met at the end of a potential plan.
Okay.
Crucially, it also includes rules that essentially prevent the solver from finding an answer set where the goal isn't met. It forces valid solutions to achieve the goal.
Ah, clever.
And this part also generates the possible sequences of actions the candidate plans that the solver will then check against the rules.
So the A prologue program, EE, bundles the domain rules, the starting uncertainty, the goal, and the mechanism to check plans.
Exactly. And the magic is that the answer sets computed by the solver for this program, EP, directly correspond to the valid, correct, conformant plans.
That sounds powerful. But how sure can we be? You mentioned provably correct earlier. Does the paper offer guarantees that these plans actually work?
It does, and that's a major contribution. They provide formal theorems establishing the reliability. The main concepts are soundness and completeness.
Okay, soundness first. What does that mean here?
Soundness, which is Theorem 1 in the paper, basically says, if your action description D is SC restricted, which guarantees determinism, remember?
Like our bomb example, PD0.
Right. If it's SC restricted, then any plan you extract from an answer set of the cautious encoding EP is guaranteed to be a correct solution to the original conformant planning problem.
So if the solver gives you an answer, that answer is a valid plan that will achieve the goal despite the initial uncertainty.
Yes. You can trust the output. It won't generate faulty plans under those conditions. It's a strong guarantee.
That's huge for building reliable AI. What about completeness? Theorem 2.
Completeness is about whether the system finds a solution if one actually exists. Theorem 2 provides a guarantee, but for a slightly more restricted class of problems.
Ah, okay. What kind of problems?
Specifically for problems where the action description has no state constraints, LFP, and where the dynamic causal laws, E causes LFP, have no preconditions. P is just true.
Simpler domains, basically.
Yes. For those kinds of problems, Theorem 2 says that if a conformant plan does exist, the cautious encoding EEP will have an answer set corresponding to it. The system won't miss an existing solution.
Got it. Soundness means the answers are right. Completeness, for some cases, means it finds an answer if one exists. So practically, how would you use this?
The method is pretty straightforward. First, make sure your action description is deterministic. Being SC restricted is a good way.
Check.
Second, you need to decide on a maximum plan length. How many steps are you willing to consider? Let's say N.
Okay, set a limit.
Then, you generate the cautious encoding E for that length N and feed it to an ASP solver. Well, pretty much. If the solver finds an answer set, great. You've found a correct conformant plan of length N or less. You might start with a small n and increase it to find the shortest plan.
And if it doesn't find one?
If it finds no answer set for length N and your problem met those completeness conditions, then you know for sure no solution exists within that length.
Okay, that's a clear process. But, you know, a plan could be correct, but maybe not very elegant or efficient. Like, in the bomb example, maybe the plan involves flushing a toilet that's already clean.
That's a great point. A correct plan isn't always the best plan in a practical sense. It might have useless actions.
So can you refine them? Make them better?
Yes, and this is another neat feature. You can add extra constraints to the A prologue program.
Yep.
You go from EP to EPC, where C represents these additional requirements.
What kind of requirement?
Well, back to the bomb example, you could add constraints like, don't dunk a package if you already know it's safe, doesn't have the bomb.
Makes sense. Don't waste effort.
Or don't flush a toilet if it's already known to be unclogged.
Avoid redundant actions.
Exactly. Or maybe just a general constraint against unnecessary flushing actions.
So these constraints prune out the less desirable correct plans.
Precisely. They guide the solver towards solutions that meet not just correctness, but also these additional quality criteria. And there's a bonus effect.
With that.
Adding these constraints often narrows the search space. It gives the solver fewer options to explore.
Ah, so it can actually make the planning process faster, too.
It often does. So you get better quality plans and potentially faster solving. It's a win-win.
That's really practical. Now, this leads to something you mentioned earlier, elaboration tolerance. This sounds really important. What's the idea here?
It is, I think, one of the most powerful aspects of using ASP for this. Elaboration tolerance is basically the system's ability to gracefully handle new information, new rules, or changes to the problem description without requiring a massive overhaul.
So you don't have to rebuild the whole thing from scratch if something changes. That's usually a huge pain point in software and AI.
Exactly. It makes the system much more adaptable and maintainable.
The paper gives some great examples.
Like what?
Well, example 2 imagines you learn a new fact about the plumbing. If toilet 1 is clogged, then toilet 2 also gets clogged.
The state constraint we talked about earlier.
Right. You just add the AL rule, clogged 2, if clogged 1, to your description D. Since this still keeps the description SC restricted.
It's still deterministic.
Yep. The encoding method, EP, handles it automatically. You just add the corresponding rule to the aProlog program. No fundamental change needed.
That's smooth. What about more complex changes, maybe to the initial situation?
Example 3 touches on that. Suppose packages come from different organizations, good or bad, and you know that packages from good organizations are always safe, not armed.
Okay, new background knowledge.
You can just add a rule like armed P from PTG. If package P is from a good org, it's not armed. This knowledge about the initial state becomes part of the logic program ES0. Again, it integrates seamlessly. The initial state itself can be described by a little program. Very flexible. Now, the really big one, non-deterministic actions. You said conformant planning handles this. What if dunking might clog the toilet, but might not? Real-world uncertainty.
Yes, this is a huge leap shown in example 4. AL can represent this. You'd write the causal law as dunk, PE, causes, clogged.
That curly brace notation means one of these outcomes happens, but you don't know which.
Exactly. It represents non-determinism. Dunking causes the toilet E to either become clogged or become not clogged, or stay unclogged. And the really elegant part,
What's that?
the way they encode this in aProlog is a relatively simple modification. And crucially, the soundness result still holds.
Wait, really? Even with uncertain actions, the plans are still guaranteed to work.
Yes, the system finds a plan that achieves the goal regardless of which outcome of the non-deterministic action actually occurs at runtime. It finds a plan that's robust against the action's own uncertainty.
That is genuinely impressive. Okay, so let's recap. We've seen how answer set programming provides this really solid, adaptable foundation for conformant planning.
Right. Allowing systems to generate plans that are provably correct.
Even when they start with incomplete information about the world.
Or when the actions themselves don't have perfectly predictable outcomes.
And this isn't just some theoretical exercise. It really impacts how we can build intelligent systems, agents that can actually function effectively in the complex, messy, uncertain environments we live in.
Absolutely.
Yeah.
And maybe thinking about this connects back to us, too. Think about the plans you make in your life or at work.
Yeah.
How often do you really have all the facts? How often do things go exactly according to plan? Probably not that often.
Definitely not often enough.
So these principles from AI, thinking about conformant planning, about being elaboration tolerant, maybe they offer a useful perspective for us in dealing with uncertainty.
That's a great point. Which leads to maybe a final thought to leave folks with. Given how much uncertainty and, well, incomplete information is just baked into our world, how could understanding the way these AI systems cope with incomplete initial situations and non-deterministic actions, how might that help us cultivate a more adaptable, more resilient mindset in our own planning, our own decisions?
Something to definitely think about. How can we build plans that are robust, even when we know we don't know everything?